teste. Tudo certo. Okay, so we will start the third class. So just a quick reminder for what I saw yesterday. Reminder. Okay, so we are studying here Ising models. So they are defined by these Hamiltonians. I'm doing this again because we have a new colleague here today, Diana. So I will just define the objects again. That is functions, or it's a family of functions that are defined for every finite subset of ZD. These are functions that take one configuration of plus ones and minus ones in a finite set to the real line. And for now on, we will concentrate on two examples. Every time I speak about Ising models, I will be thinking mainly in two examples. And one is they all have this general form here. Their Hamiltonian are described by this expression. I will consider H to be constant. I will also put beta here, where beta is the inverse temperature. And also, the examples that we will have in mind are the nearest neighbor Ising model, where jxy is j, j if the distance between x and y is equal to 1 and 0 otherwise, or jxy is equal to j times the distance to some power alpha, if the distance is not 0 and 0 otherwise. Okay, so and alpha is larger than d, and also j, the constant, is always positive, so we are in the case of a ferromagnetic system. We defined the local pressures using local pressures using partition function. So the partition function depends on the finite set, on beta and h, and it's just the sum over all configurations, all possible configurations, of exponential of minus h lambda sigma, where we will make the dependence on beta and h explicit in this way. Beta and h. So the local pressure was defined as lambda. Oh, sorry. P lambda as being 1 over the size of your finite system, and you take the logarithm of the partition function. Okay? So what I showed yesterday was that the existence. We showed the existence of the thermodynamic limit. Thermodynamic limit. You know what this means is that if I take a sequence of finite sets, finite sets converging to ZD for any sequence converging to ZD, we have that the limit of the local pressures as a function of beta and h. Okay, so this will be a function of beta and h. This actually converges, and they all converge to the same number that we call the infinite volume pressure. Okay, so as we were talking about in the first day, to model phase transitions, we are trying to we need to find some kind of bad behavior of some thermodynamic quantity such as the pressure. And the problem is that when you stay this kind of bad behavior, you can understand as the failure of some derivative of this function to exist. So, and the first problem that you get when you stay in a finite volume is that all the derivatives exist. And actually, the derivative has a very special expression, and we will do it right now. So let us take the derivative with respect to h. Okay, so what happens in this case? So if you take the derivative with respect to 8 of this expression, you get something like this. You get 1 over the size of lambda, okay? And then you have to derive the log. So you get 1 over the partition function, beta h, times the sum, times the derivative, okay, in h of the partition function, beta h. And what this is 1 over lambda times 1 over the partition function. And this, we just have the expression here. So by take the derivative we have with respect to h, the Hamiltonian is something like this. We get, since there is a minus there also, we will have the sum over all the configurations. And then we get another sum of all the spins located in the finite volume times exponential of minus h lambda beta h sigma. As you can see, this quantity right here, if you have your ferromagnet, if you take a look at each one of the spins, what you are doing here is that you are summing for some configurations all the possible orientations of the spin. So this will be called, this we call m lambda, the total magnetization. But we actually have a 1 over the size of the finite set. So what we can define also is also what we can also define is the mean magnetization as being this quantity. The main magnetization. Okay. So I know that many of you already know a little bit about Gibbs measures, but what happens here is that this is a function of the configuration space. And since I have the partition function dividing this whole thing, this looks like an integral of this function. And more than this looks like a probability measure because it is normalized by this. So if I can define a probability measure on this space. And remember, since lambda is finite, this is also a finite set, although a large one, it's still finite. And so I can define a probability measure by just giving the probability of each one of the configurations. So if I define this probability measure here, the probability of a configuration should be the exponential of minus beta h lambda, oh, there is no beta here, sorry, h lambda beta h here, divided by the partition function. Then I can write this expression as an integral with respect of that probability measure. So I can write the first derivative with respect to the field of the local pressure as being an integral, right? Of the mean magnetization, that quantity, this quantity right here, with respect to this weight given by this probability method. So beta h sigma. Okay, so for now on, we will introduce a notation for quantities like this. I will write it. Okay, we will write it for any function on the configuration space. Okay. We write like this: the mean of f with respect to this probability, with respect to this probability measure, we will write it like this. So this is, sorry. Sorry. It's only on the two-bar interaction. I write the Ising Hamiltonian as beta jxy h sigma x. The beta is here. I didn't put the beta. It's here. So yeah, this is quite unusual because in this way it's easier to show something like convexity and stuff like that. So okay. So yeah, it's inside of h. It's inside of h. sigma beta h sigma. Okay. We also, of course, this definition, there is nothing special with respect to the empty boundary condition Hamiltonian. Yesterday we defined also what it means to be to have a boundary condition. Okay. So similarly, we can make the same definitions Similarly, we can make the definitions of the finite volume Gibbs measure. I will call it like that already. This is the name. It's the finite volume Gibbs measure. So something like this. For every boundary condition. For every boundary condition, I can define also a similar weight beta h sigma over the partition function. Okay. I can make a similar, I will introduce also a similar notation to the mean of any function with respect to this probability measure, beta h omega sum mi lambda beta h omega sigma. Okay. And just for you to remember, the boundary condition is introduced. The Hamiltonian with a boundary condition is introduced in the following manner. You sum the empty boundary condition Hamiltonian. You add a term that depends x inside lambda, y outside lambda, j xy sigma x. And since the configurations only live on this space, I need to say what's happening outside lambda c, so I use the configuration omega that is fixed. Okay. So a similar relation to this one also holds for any local pressure with boundary conditions. Okay. So, and as you can see, I could continue to take derivatives. So first exercise of today. Exercise. Calculate the second derivative with respect to the field beta h, and the first one with respect to the temperature, the inverse temperature. Just so you can get a feel of what is happening. So I can give you a spoiler, a little bit of a spoiler. Turns out that this quantity is very important for the Ising model. Actually, everything that you want to know about the system comes from studying what happens to this quantity with respect to a Gibbs measure, to the So, okay, and the second derivative, the first one is a mean. The second derivative will be something that they call the variance of this variable, uh, this quantity right here. And actually, if you continue to take the derivatives, you have also some nice probabilistic interpretation to each one of the derivatives of the local pressure. So, okay. Do you have, okay. So, what I want to talk about today is continue to explore a little bit more of the pressure. Some properties, some other nice analytic properties of the pressure. And to show, to use this as a kickstart to study, to abandon the study of the pressure and go only to the study of the measure. So the first thing that I want to show is the following. The pressure have a nice property called convexity. I know that maybe not every one of you heard about this, so I want to give you a little introduction about some important results of convex functions. So first, what is a convex function? So definition. If you consider a function from an open subset of Rd open, then you call it convex. Convex if and only if the following property is satisfied. If every time, if this is U, this is your set U, and you take any x and y, okay, you can write any point in a straight line connecting x to y as something like this. So for any point, let's say z in the middle, that will exist a lambda, a real number, between 0 and 1, such that z is equal to lambda x plus 1 minus lambda y. So you can see when lambda is 0, you are in the beginning of the line, and when lambda equals to, yeah, it's the other way around. If lambda is 0, you are in y, and if lambda is 1, you are here, okay? So you write every single point between this line as some combinations like this. We call this a convex combination. So a function will be called convex if for any point like this, so for any convex combination, the function satisfies this inequality. X plus 1 plus fy. And this is a very important property. This is a very important property of that a function can satisfy. And actually, the pressure satisfies this. So I will show the first proposition of today is that the pressure the local pressure is convex. So what this means that if I take lambda inside, so let's start the demonstration. If I take lambda inside this one, this interval, otherwise for the extremes of the interval, the inequality is trivial, okay? So we just need to check on the open interval. So the local pressure for any lambda in this interval, 0, 1, we have the following. If I write P lambda, and here I have lambda beta 1 H1 plus 1 minus lambda beta 2 H2, okay? I will have, this is exactly the pressure with a convex combination of the inverse temperature, P beta 1, P beta 2. Okay? And what is this? I know exactly what this is. This is 1 over lambda of the sum of exponential, of over all the configurations in your configuration space of E minus H lambda depending on the convex combination. Beta 2 lambda H1 minus lambda beta 2 H2. Okay? But if you remember the expression of the Hamiltonian, you can notice that H is splits like that with respect to this convex combination. It will be plus 1 minus lambda beta 2 lambda H1 plus 1 minus lambda H2. This is exactly lambda times the Hamiltonian of the Ising model with parameters beta 1 H1 plus 1 minus lambda H with parameters beta 2 H2. And so since I have this exponential function, what I can get is that using this decomposition is that the local pressure is 1 over lambda times the sum exponential minus, lambda beta 1 H1 all to the power lambda times the exponential of minus H lambda beta 2 H2 1 minus lambda. Okay, so what we do from here? So we need to use something that I guess some of you already heard of, is the Holder inequality. So the Holder inequality. What is the Holder inequality? If I let x and y be points in Rn, okay, and I choose, okay, this will not work here, so I will write it here. The holder inequality. So if I take x and y inside RD, okay, and I take P and Q in the interval 1 plus infinity, but I allow it to take the value plus infinity, such that 1 over P plus 1 over Q is equal to 1, okay? Then the following holds. Then the following holds. So the sum over 1 to some n, okay, of the product, the absolute value of the product of the coordinates of x, y, of x and y, this will be less than the sum of 1 to the n absolute value of x, y to the power p, 1 over p, okay, times the sum 1 to n to the power q, 1 over q, okay. So we actually need this quantity to this inequality to finish, because what we have here is something very similar to this situation, okay? Because you have because these are all positive numbers, okay? So this is the absolute value of this will be the xy. The n, the dimension of the space, is the dimension of the configuration space. And then by applying this inequality, applying holder, we have the following. So this will be the sum of exponential. Okay, so I need also to show you what is the choice of P and Q. So I will apply the holder inequality, and the P will need to be 1 over lambda, okay? Since lambda is between 0 and 1, so P will certainly be here, okay? And Q will be 1 minus 1 over lambda. So, okay, so now we apply the inequality, and we get the star will be less than the sum. I will ignore this term right now. So just look to this one, to the sum. Sorry. One over 1 minus lambda. Yeah. Why did it? There is a problem with this choice? Okay, so the thing is, wait, just a second. So 1 over P should be lambda, okay? So 1 over Q should be 1 minus 1 over P, and P is 1 over lambda, okay? Yeah, the sum of the inverses is equals to 1. Oh, yeah. Oh, sorry. 1 minus lambda. Yeah, exactly. So P is 1 minus lambda, so Q will be, okay, what, like this. Yeah, okay. So what we get is the sum over sigma exponential of minus beta h v1 h1 is not beta here, it's lambda, okay? But I will multiply it by p, okay? So p is 1 over lambda, so this disappears. This to the power of 1 over p, so to the power lambda. Okay, so there is another mistake here because there needs to be 1 over lambda, the log, okay? 1 over lambda, the log here. Okay, so going back to the sum, we have this here. 1 minus h lambda beta 2 h2. And again, the same thing happens. The Q is like this, like Kelvin noticed. And then you kill this part right here. And then you take this to the power 1 over Q. That will be exactly 1 minus lambda. So when you take the logarithm, when you take the log, you will get that this is exactly the partition function. This is the partition function with respect to beta 1 h1 to the power lambda. This will be the partition function with respect to beta 2 h2 1 minus lambda. And when you take the logs, you get that the log of z, the convex combination, I write it right there. That's the log of the partition function with respect to the convex combination, beta 1 plus 1 minus lambda beta 2 lambda h1 h2. And this will be less than the convex combination of the logs. Beta 2 h2. And then when you divide by the volume of the box, you get exactly the result. So that P lambda, the convex combination, beta 1 h1 plus 1 minus lambda beta 2 h2 is less than lambda P beta 1 h1 plus 1 minus lambda P beta 2 h2. So, okay, this quantity is convex. And the first thing that we can notice is that if I have a sequence of functions, continuous functions, converging pointwise in this case to some limit, And this limit, and each one of the points in this sequence, the functions in this sequence, are convex, then the limit will be convex. So the first corollary that we get from here is that the infinite volume, the pressure in the infinite volume, P beta H, is convex. Sorry. So what are the consequences of such property? So remember, we were talking about in the last 2 days about how could we find some bad behavior of this function. And turns out that if the function is convex, there are some kinds of bad behavior that are not allowed to happen. And the first one is continuity. So the first one is continuity. So every convex function, so consider f a function from an open subset of Rn, convex, convex. Then it is continuous. Then it is continuous. So, okay. So, I will let this to be an exercise, okay? This will be an exercise. If you have any questions with regarding to this, you can ask me. Actually, the proof is quite straightforward. And since the thermodynamic limit of the pressure is also convex, this means that the pressure is automatically continuous with respect to beta and h. Okay, so the only hope that we have to find some kind of bad behavior is to try to study the derivatives of this function. Okay, but turns out that if you have a convex function, these functions are not only continuous, but they satisfy another very important property, and this property is that that every right and left derivative, partial derivative, will exist. So we will show this. So property. Every left and right derivative of the pressure exists. So since this is a general property of convex function, I will prove this proposition for every convex function, and then as a consequence we have the same property for the pressure. Okay? Okay. Let us start with another exercise. if f from now I will consider an interval f to be an interval to R, an open interval. So it could be an infinite open interval. And I have three numbers x, y, and z that one follows the other like this. One is larger than the other. Then is convex. We have the following chain of inequalities. Fy minus fx divided by y minus x is less than fz minus fy z minus y, and this is less than fz minus fx z minus x. Okay. So I will use this property of convex functions to show the existence of the derivative. So to show the existence of the right side derivative, I will consider decreasing sequence Hn of real numbers. Okay, real numbers that are converging to zero. So the limit of Hn goes to zero, is equals to zero. And what this property shows me is that for any x in the interval, in the domain of the function, what we have is that x1, I will need this to be positive, okay? So they are decreasing and they are positive, okay? And what I have is that if I take x in the interval, then x is less than x plus hn for every n, okay? And since the interval is also open, this means that there will be some very small epsilon positive, where x minus y minus epsilon is still in the interval. So I have this. So epsilon positive such that this is still on the interval. This is true because the interval is open. So now I can apply these inequalities for this chain of real numbers, and I will get the following. So I can get that this one in the middle will be this minus this, so f x plus hn minus f h, okay, divided by this minus this, it will be only hn. This is larger than this minus this, so fx minus f epsilon. But this holds for every n. For every n. So the sequence given by, so the sequence given by minus fx over hn is lower bounded by something fixed. So have a lower bound. Have a lower bound. Have a lower bound. And more than that, since the sequence is decreasing, this means that if I add to x hn minus 1, the previous member of the sequence, then it will be larger than this one. So I can apply again this property here, but now choosing the following. I have this minus this, so x plus hn minus 1 fx over hn minus 1. So this minus this term right here is actually larger than this minus this one right here. So in this case, it will be larger than x plus hn minus x hn. So I have a so this sequence, it is lower bounded, okay, and also it is decreasing this sequence here. So it will have a limit. So it's lower bounded and decreasing. Therefore, it has a limit. Okay. But notice that I considered any decreasing sequence. So this implies the existence of the right derivative, the right side derivative of f. Okay. So I have okay. So a similar argument holds also for the left side derivative. Similar argument holds for the left side derivative. Okay. So now this one you can use to prove the you can use you can use to prove continuity here also. You can also use this to prove a continuity here, but if you don't know how to use this to prove continuity, you can also, yeah, there are many ways to prove continuity if you have convexity. So, okay. Now, another property that is actually interesting, and we will use it, is the following. Notice that in the definition of pressure, I guess I erased it. So in the definition of the pressure, we have a limiting procedure. Okay? So the pressure, okay, my chalk, okay, here. So in the definition of the pressure, we have a limit. In the definition of the pressure, P beta H, I actually have a limit. Okay? P beta H lambda n. Okay? I actually have a limit. I know that since the pressure is convex, at least the partial derivatives with respect to the right and the left side, they exist. But I want to make a connection with what happens to the derivative of this, the pressure, with respect to the derivatives of the local pressures. So what I wanted to do, what I want to be able to do is the following. What happens if I consider this, and if somehow I can interchange the limit? First, if this exists, the first question is that if this exists, we only have the existence of the right and left derivative. We don't have right now the existence of the derivative. But if this happens, can I relate this to what happens with the derivative inside the limit? And just for us to remember, if I can interchange the derivative, if it exists, with the limiting procedure, with the thermodynamic limit, then I will be able to relate the derivatives of the pressure with the thermodynamic limit of the quantities that we defined previously. So what are these quantities? The mean magnetization, the mean of the mean magnetization, right? With respect to some object, beta H, to some object that we will study with much more care during this course. Because if all of this that I said to you, I can show that I can do, the derivatives exists, I can change the limit of the derivative with the thermodynamic limit, then I have this remaining problem to give you what is the meaning of this quantity right here. So we will we'll go forward by small steps, right? And first, I will show you how to. I will justify first why I can change these limits. Okay. If the derivative exists. So, okay. First proposition, if Fn Again, functions on an interval, okay? E open interval, an open interval, such that Fn converges pointwise, to some f. This means converges pointwise. And f is differentiable at some point x in the interval. Then I have the following property. The limit of the right derivative is equals at x, right? Yeah, at x. Now, okay, is equals to the limit of the right derivative of the left derivative fn x, and this is equal the derivative of f at x. Okay. So to not make any confusion, I will use another notation, f prime x. Okay. So if this, if I can prove this, then this procedure here will be justified every time the pressure is differentiable at some point. Okay, so let us demonstrate this fact. Again, we will use the property that I just erased, that is very important. I will write it right here again. So remember that for every x less than y less than z, I have fx, fy minus fx, y minus x is less than fz minus fy, z minus y, and it's less than fz minus fx, z minus x. Okay? So, okay. So, consider sorry. Yeah, they all need to be convex. Yeah, if it, okay. So a function, a sequence of functions, okay, that are convex. If fn convex. Yeah, this is important because I just showed you that these quantities right here, the left and right derivatives, only exist. They are guaranteed to exist when the function is convex. So yeah, I need each one of the function of the sequence to be convex. So okay, so what we do is that again consider Hn again, sequence of positive real numbers. Real numbers, decreasing to and converging to 0. Okay, so what we want is the following. So take x, the point. Take x, the point inside the interval, where we know where f is differentiable at this point. Differentiable. So what we have is the following: for every k positive integer, for every natural number, it will hold the following. So fk x1 plus hn minus fk x divided by hn. Okay. This will actually be less than, let's say, I also need, okay, and let's say that they are decreasing. Okay, so the largest one is h1. Let's say that h1 is less than t, some real number. Okay, some parameter t. This decreasing t is larger than any of the members of that sequence. T, a real number. So what happens is that then x plus hn will be less than x plus t, and this will always be larger than x. Therefore, we have the following. This minus this is exactly this term right here. This one will be less than this term here. It's fx, fk, x plus t minus fx divided by t, fk. So now we can consider the limit with hn going the limit in n in at both sides. Okay, and the limit in n doesn't affect this part of the inequality because it doesn't depend on n. So this will be exactly the right side derivative of x of fk at the point x, and this will be larger than be less than, actually it will be less than fk x plus t minus fk x over t. Okay, now I can't for sure guarantee the existence of the limit in k, but I can guarantee the existence of the link sup of the sequence in k, the link sup of in k. And since link sup here also, but since the functions converge to f pointwise, I know exactly what this limit is, and this limit will be fx plus t minus fx over t. Now I can take, again, since the function f is differentiable at x, and I have this inequality that holds for every t. Now there is no information on the sequence and whatever. Then I can conclude that the link sup the x plus x fk is actually less than the derivative of x of the derivative of f at the point x. Okay. So now we need So now we need to prove another inequality because I have only one part. I need to analyze what happens to the left hand side, the left side derivative. So again, consider a sequence, a decreasing sequence, just like this. So consider again a decreasing sequence of real numbers. Hn. Okay. And enlarge this one. Such that the limit is also 0. The same thing as before. And I will also suppose that they are all they are upper bounded by some t, the same way I did before. But now I will make a trick, let's say. So I know that because of this property right here, I know that minus t will be then less than minus hn. So if I sum x, I will have something like this. But if hn is, since hn is a positive sequence, is a sequence of positive real numbers, then this will also be less than x. Okay. So I need to use a similar trick that I did before, and this trick is I consider this minus this, so this fk. So for any k a natural number, it holds x minus t over t actually I guess it's the other way. It's the other way. Just a second. The other side. Just a second. I need it to be oh no, sorry. It's not this. It's not this one. I know that this one, hn, fk, hn, minus fx minus t. So this one right here So this one right here, fk, x minus tn, hn, minus f, x minus t, fk of t minus hn, that I know this is strictly positive. This will be less than, I choose this one and this one. This will be less than this one minus this one. So will be less than fx, fkx minus f, x minus hn, fk over hn. So again, since these functions are convex, they are continuous, as we talked earlier today. Since this is converging to f, the f will also be continuous. So we can use the continuity of each one of these fk, since they are convex, to take the limit with respect to n in both sides, on both sides. Limit with respect to n. But since this sequence now is approaching x from the left, this will be the right side derivative. This will be the right side derivative of f in the point x. And this will be less than, now fk x minus fk x minus t over t. This is a very similar situation. So what else we can do? So now the sequence is upper bounded by the left derivative. So if I take the lim inf instead, so if I take the lim inf fk x minus fk x minus t over t, if I take the lim inf with respect to k, this will still hold. So what I get here again is that since f is converging to, since fk is converging to f, this will be exactly this. And then I have a similar result. Then this implies that the link sup, yeah, the x plus fkx with respect to k is less than f prime x, that it's less than the lim inf of with respect to k, the f xk here. Okay, so we are almost done. We need one last result that again will use, it will use this property right here. So we get that I just did this, so I will go to the other way, to this way right here. Okay. So if x, okay, then for any for x you consider t positive, such that x minus t less than x plus t. Okay. And then what we have is that we get that x plus t minus fx. Okay. So what happened now is the following. I prepare until now the class. I was hoping, can we stop the recording? Cut. So, o que acontece é o seguinte, essa aula eu preparei para ontem. E hoje, eu achei que ela ia ser suficiente, porque ontem eu dei mais metade. E ainda sobrou meia hora.